Okay, so in this section, we're going to take a look at one of the main reactions that esters themselves can undergo, and that is known as the hydrolysis of esters. And whenever you see the term hydrolysis, you're going to see this a lot here in organic chemistry, but you're also going to see it in biology. Hydrolysis comes from two words, meaning hydro and lysis, right? So lysis there means the splitting or the breakdown. And then hydro meaning using water. Right? So hydrolysis of something means the breakdown of it using H2O or in solution. So there are two ways by which we can hydrolyze or break down an ester. And we're going to see both of these here. We're going to be looking at the hydrolysis of an ester under acidic conditions. And then we're also going to see it under basic conditions. Right? And the names kind of tell you what's occurring. Acidic conditions would involve the use of an acid. And basic conditions would involve the use of a base. And then the products are going to be slightly different in each case. So under acidic conditions, what we actually end up doing is just the opposite of esterification. And we end up producing the original carboxylic acid and the alcohol. All right, and that's the one we're going to take a look at first. So under acid hydrolysis, the ester is going to react with water and we're going to need an acid catalyst for this to happen. We're also going to need a little bit of heat for that process to happen. And we end up producing the original acid, carboxylic acid, and the alcohol. All right, so if you take a look at this reaction, it is just the opposite of esterification that we saw in the previous section. Right, and we're going to see this a lot. We have actually seen this already in organic chemistry, where reactions can go both ways by simply changing the conditions. So if you notice here, when we saw this arrow as well, when we looked at esterification, it's a forward and backward arrow, meaning that it's reversible, right? So in the esterification reaction, we saw that we could combine a carboxylic acid with an alcohol to make an ester and water. Now we're saying we can take that ester, add it to some water, provide some heat and an acid to it, and then that'll break it down back into the original carboxylic acid and the alcohol. So just the opposite of esterification. So the water molecule in this reaction is going to provide the OH group to convert the carbonyl of the ester into the carboxyl group. And then the other H from water is going to go to the alcohol itself. All right, so if you take a look at an example here, we have our ester methyl ethanoate. And again, what you want to do is to identify that ester bond, and we're going to break it right down the middle. All right, so there's the ester bond. I'll highlight it in yellow. And we're going to break it right down the middle. All right, and that tells us which part came from the acid. So the carbonyl part of it, the left side in this case, is going to be from the acid. And then the other part is going to be from the alcohol. So the OH then, that comes from water. Remember, water is HOH. You can think of it as looking like that. An OH from the water gets stuck onto that carbon, and then the remaining H from the water gets stuck onto the O here from the original part of that ester, right? So we end up attaching the OH from the water molecule to that carbonyl carbon, and then we end up attaching the H from the water molecule to that O. All right, so the key thing here is we're going to split the ester right down the middle. Right, that's where it's being broken. And the products that we get would be the original 2-carbon carboxylic acid, which would be ethanoic acid. We have a 1-carbon alcohol, which would be our methanol. So that's the acid hydrolysis of an ester. It's just the opposite of esterification. And in that case, we're going to get the original acid, carboxylic acid, and the alcohol. Under basic conditions, so basic hydrolysis, there's another term that we use in organic chemistry to represent those conditions. We say that we're subjecting the ester to saponification. And saponification is just a fancy word that means soap making, because the basic hydrolysis of certain esters actually results in the formation of soaps, and we're going to see this in the next chapter. So basic hydrolysis or saponification involves the reaction of the ester with a strong base in the presence of heat. All right, and the products that we're going to get under basic conditions are going to be different than what we saw under acidic conditions. All right, so under basic conditions, we're going to have our ester now plus a base with a little bit of heat is going to give us the salt of the carboxylic acid. And we're also going to get the original alcohol. Right, so the difference here in the products compared to the acid hydrolysis is this thing. All right, so under acidic hydrolysis, we actually got the original carboxylic acid. Under basic conditions, we're going to get the salt of that carboxylic acid. We saw salts of carboxylic acids in the previous chapter. So let's take a look here at an example. We have the same ester that we used previously, right? Methyl ethanoate. And we're going to identify the ester bond just like we did before. So there it is. And we're going to split it right down the middle. All right, just like we did previously. We're going to split it right after the C double bond O, the carbonyl. And what's going to happen next is the H from the base, the sodium hydroxide in this case, right? That gets attached to the alcohol part of the ester, and then the NaO part of the remaining part of the base gets attached to the acid part of the ester. All right, so we end up now try to color code everything. All right, so we end up forming our salt of the carboxylic acid on the right side. And then we also get the original alcohol, which is our 1-carbon alcohol, which would be methanol in this case. All right, remember the salt of the carboxylic acid would be the anion, the carboxylate anion, and then we also have the corresponding cation attached next to it. In this case, the NaO from the sodium hydroxide provide both of those. All right, and when we name our salt, right, it's the sodium, the cation first, and then the carboxylate anion second, which in this case would be ethanoate. So let's take a look at a couple examples here to reinforce that concept or that idea of the acid hydrolysis and the basic hydrolysis. All right, so you want to first of all be able to know those conditions, all right, that tell you whether something is undergoing acidic hydrolysis or basic hydrolysis. So let's see here. It says, write the balanced equation when methyl acetate, All right, so that tells you it's an ester right away. Methyl acetate is also, you could also name it as methyl ethanoate, right? Because ethanoate is the IUPAC name for acetate. That's a 2-carbon part of the molecule, and it's reacting with water, heat, and an acid catalyst. All right, this suggests then that this would be acid hydrolysis. All right, so let's draw that ester first, methyl acetate or methyl ethanoate. All right, so remember in the ester, the last name, which is the ethanoate part of it, came from the carboxylic acid. So I like to draw that first. So 1, 2. So there's my acid part of the ester, and then that's connected to a 1-carbon alcohol, which would look like that. All right, so if I were to color code this, this is my methyl. That's this part of it over here. And then my acetate part of it in green, that would be this region here. And then my ester bond would be the bond in blue, which would be this bond here. All right, and then we're subjecting it just like we did in the acid hydrolysis. We're reacting it with water under acidic conditions. So plus H2O. And you want to think of H2O as HOH. All right, so again, when you think of your ester, we're going to split it right down the middle, right here. And the H from the water molecule gets attached to the oxygen here that is on the alcohol side of the ester, and then the OH from the water goes to the carbonyl carbon here of the acid part of the molecule. All right, so when we draw, again, draw everything that doesn't change. Let me redraw that really quick. So we have my 2-carbon with the carbonyl, and then I'm going to attach to that now an OH. And then I have the alcohol that's going to be produced, which is just a 1-carbon alcohol, which would look like that. And if you want to, you can draw in the CH3 here just to put your mind at ease. All right, so we have our acid, our original acid, which is methyl ethanoate. And when we subject that to, our ester, methyl ethanoate, when we subject that to acid hydrolysis, we end up with the corresponding carboxylic acid, which would be ethanoic acid. And we get the corresponding alcohol, which would be methanol. Under basic conditions, the products are going to be different. All right, like we saw previously. So what tells you these are basic conditions again are the reagents or the conditions. So we have potassium hydroxide, which is a base, right? And it's a base because it contains a hydroxide ion in it, right? That suggests that this is going to be basic hydrolysis. All right, so again, we start off with our ester. Now we have our potassium hydroxide, KOH. Going to subject that to some heat. All right, and again here we're going to break or split our ester right down the middle. The H here from the potassium hydroxide goes to the O of the alcohol portion of the ester, and then the remaining K and O go to the carbonyl. They get attached to that carbon of the carbonyl. So if I were to draw everything now, that doesn't change. There's the O and the K from the base, the potassium hydroxide, and then my alcohol again ends up being the same alcohol as I did previously. I get methanol as my product. All right, so if I circle everything here that changed and try to color code it. All right, that's where everything goes when that reaction happens. And if we were to name those products, all right, I know you didn't have to in this question, but we should name them. The salt of this carboxylic acid would be potassium ethanoate, and then the alcohol will be the same one as we saw previously. This would be methanol. All right, so those are the two main types of reactions that your esters are going to undergo. They're pretty much subcategories. So hydrolysis is the main reaction. Under acidic hydrolysis of an ester, we produce the original acid, carboxylic acid, and the alcohol. Under basic conditions, we produce the salt of the carboxylic acid and the original alcohol.